Hello everyone, my name is Denis Antipov, and in this video I present you our work with Benjamin Dare on how to analyze the evolutionary algorithms precisely on plateaus. So plateaus are some areas of the search space where we have a constant fitness, and for example consider a one-max problem where we must divide the vertices of some graph into two sets to maximize the number of edges which go from one set to another. So consider this instance where the cut is shown with this dashed line, and you can see that any one bit mutation which moves one vertex to another side of the cut doesn't change the number of the cut edges, but only then we can move another vertex to another set to increase the number of the cut edges. So to study how the AAs behave in such plateaus, we define a pseudo-Boolean benchmark function, plateau, k, which resembles the one max function, except it has a plateau of the second best fitness in radius k around the optimum. This function was inspired by another benchmark function, jump, which brought us a lot of useful theoretical results on how the algorithms cope with local optima. So we consider how a simple evolutionary algorithm, the 1 plus 1a, optimizes this function, but we allow this algorithm to use any unbiased mutation operator. The only constraints we have is that we consider only plateaus of constant radius, and we also say that the used mutation operator must flip exactly one bit with at least some sub-constant probability, which is quite a natural assumption. So in this setting, we got the result that the expected runtime is exactly n into k divided by k factorial, and by the probability that we flip between 1 and k bits, multiplied by some factor which is very close to 1. So we know that this is an equation because we also got the estimates on the distribution of the runtime. But not to overload you with this complicated formula, we can just say that the runtime follows a distribution which is very close to the geometric one, with parameter p, where p is k factorial over n into k multiplied by the probability that we flip between 1 and k bits. Our result is consistent with the previously result obtained by Garnier and co-authors for the needle function, where they showed that the 1 plus 1a with the standard bit mutation or with the 1 bit mutation has this runtime. And we note that in both cases, the expected runtime is the size of the plateau divided by the probability to flip a positive number of bits, which is not larger than the radius of the plateau. So, however, the behavior of the 1 plus 1a in both cases is very different. So when we have a restricted plateau, we waste a lot of iterations when we generate an individual outside of the plateau, and thus we don't move around. While here, in the needle function, the algorithm performs a random walk around the search space. So from our main result, we deducted several corollaries. For example, we showed that the optimal mutation rate with standard bit mutation is k over en, and it gives us constant improvement in the runtime compared to the standard recommendation of 1 over n. We also showed that it is a good idea to use the 1 bit mutation because it maximizes the probability that we flip between 1 and k bits. And we also spread our results on some hyperheuristics when we can choose the mutation operator according to some strategy. So, but in general, we showed that the exact choice of the mutation operator cannot change the expected runtime drastically. It can only change by a constant factor. So in our analysis, we used the Markov chains, and we represented the plateau with a distance levels Markov chain, where each state corresponds to the distance of the current individual to the optimum. So we considered the distribution over the states of the plateau. So we had some initial distribution pi, and then it changed through the time. And after t iterations, we had a distribution which equals to pi multiplied by the transition matrix of this Markov chain for t times. And then we note that the sum of first k components of this distribution is the probability that we steal in the plateau, and thus this is the probability that the runtime is strictly greater than t. So to estimate this sum, we considered another Markov chain, and the states of this chain correspond to individual. Each state corresponds to some individual in the plateau. So it means that there are a lot of states, something like n into k divided by k factorial, and this Markov chain seems to be hard to analyze, but it has some nice properties which helped us to get the main result. So more details in the paper because we are short on time. So in conclusion, this paper aims at taking more attention to the plateaus and to the analysis of them. And we have already showed that choosing different mutation operators can actually reduce the runtime by a constant factor, but maybe there are other ways to overcome the plateaus. We also showed that Markov chains can be very useful in the analysis of plateaus, and they can bring results more interesting than different advanced techniques like the drift analysis. And one of the most interesting directions of the further research which we see is studying how the population-based EAs behave on plateaus. So thank you for your attention.